All right, it's 8 o'clock on the dot. Let's get started. Good morning, everybody, and good afternoon, good evening, whichever uh, part of the world you're calling in from. We're happy to have you. Today, we will have our second tinyML talks. Hope all of you are staying safe and healthy during this lockdown. And today we'll have Sek Chai from Latent AI to talk about adaptive AI for a smarter edge. If any of you or your organizations are interested in sponsoring some of these tinyML talks, sponsorships are now available. Contact Berry at tinyml.org for more information. And we can actually have different sponsors mentioned here. A major milestone that we achieved in the past week, our Bay Area meetup has crossed 1,000 members, and we'd like to congratulate Reza Khosravi, co-founder of Galliot, who is our 1,000th member. If you'd like to join our Bay Area meetup or any of our several meetups that have opened up across the world, please go to meetup.com, the link mentioned below, and you can join the one that is geographically closest to you. Be sure to tune in next week, 2 weeks from now, actually, April 28th, for we have two talks by Professor Song Han from MIT and Alexander Aroma from Octonion. It starts at 8 o'clock, and each presentation is approximately 30 minutes in length. Please contact talks at tinyml.org if you're interested in presenting at one of the upcoming sessions. As a reminder, as Ira already mentioned in the chat window, please use the Q&A panel to ask your questions. As I moderate, I'll be looking at the Q&A window for asking questions to Sek. If you mention it in the chat window, the question may get missed. The slides and video recording will be available at tinyml.org/forums tomorrow. By way of introduction, Sek Chai is the CTO and co-founder at Latent AI. In previous roles, Sek was the principal investigator for multiple DARPA and DoD projects at SRI International, and also held senior technical positions at Motorola Labs. He received his PhD from Georgia Tech. Sek has spent most of his career focusing on evangelizing efficient computing for embedded vision. Welcome, Sek, and go ahead.
All right, thank you, Ravi. Hello, everybody. Thanks for joining in. This talk is the second talk in the tinyML Talks webcast. So very appreciative last week when we had Pete Warden talk about how to get started in tinyML. This talk, I'm going to talk a little bit and cover some areas more on the software side to see how we can enable some of these tinyML solutions. So it's titled Adaptive AI for a Smarter Edge. And we'll kind of cover different topics with respect to optimization, quantization for specific, and other things that leads to very important, I think, use cases towards the end. Okay. First of all, before we start, big thanks to the tinyML community. Lainey AI is a proud sponsor of tinyML. We've kind of seen it getting grassroots support, starting from scratch to where it is today, and it's growing, right? So we're a proud sponsor of it, hoping that it will grow even bigger, right? And special thanks to the tinyML organizers. I know Ira, Olga, Yugivni, Ravi, all those folks. There's a lot of work behind the scenes to get this going. And in this time where we all in a lockdown kind of scenarios, this is very important to keep everything going, keep the momentum going. So thanks for that. And also thanks for all for attending, right? It's important to keep engaged in these scenarios. And thank you all for attending. And hopefully you'll learn a little bit from what we're presenting in these tinyML talks. And hopefully you'll get to and participate and volunteer to present, as Ravi mentioned. So before we get started, I'd like to cover a little bit about who we are. Lainey AI is actually an early startup. We founded in December 2018, so we are a little bit over a year old. Not too new, but enough to get started and have things in the works. We are a SRI startup, a spin-off from SRI, And we are backed by a lot of DARPA technologies that I worked on while at SRI, right? Part of my work while at SRI. What I've taken is the technology, built on it, kind of moved it beyond the basic science with DARPA funding and into now industry, hopefully to enable other folks to use some of these technologies. Lainey AI is VC funded. Our seed round was led by Future Ventures. We are happy to have them support us and recognize that they see some impact that we can provide with the technology. The bottom line of it is Latent AI develops core technologies, ML technologies, right, that enables efficient adaptive AI. So we built tools that allow other people to build tinyML solutions, right? We want to enable other folks to be able to do what they need to do, right, to enable the solutions that are important in the future. This is the team. I like to kind of give a shout out to my core team here. Everything that you see in the presenting slides are done by the team, right? I'm here as a spokesperson of all, right? Presenting what they have achieved, what they have accomplished. Very proud of my team here. And the team is growing. But these are the core sets of folks that have joined us. And we're taking a road trip with Latent AI in a way. And just to get started, right, tinyML at the edge. We all seen these kind of ideas or pitches about tinyML. It's solutions where things are on the edge, right? They're very constrained. There's you know, reports, Gartner reports and things like that that predicts, you know, by 2025 you have 75 billions of these devices. It's everywhere, right? It's very pervasive. It's almost hidden in a way because it's so small. With these kind of tiny devices, it's kind of connected to your sensors of choice. It could be audio, video, even vibration sensors, right? These are things that, you know, you put a smart processor next to your sensor and you can do a lot of things from detection, recognition, anomaly, recognition, all those kind of things, right? And there's going to be trillions of these inferences annually. The things are just buzzing along, working to help you know, us live better, live longer, make things usable, all those kind of things that are important. The key things to this is that there's going to be a lot of these and all of it is working hard, right? Trillions of inferences annually, if not more, right? And what we want to get to then is say, if you have a lot of these devices, how do you make it efficient? How do you make it really usable with the lowest amount of memory, lowest amount of power, and things like that, right? So efficiency at the edge is all we about, right? We can certainly put, you know, big processor, you know, out there, but that's not what tinyML is about, right? It's about saying there are ways in which we can make these efficient, either algorithmically in software or in hardware. What we want to talk about in this presentation is about quantization, looking at one specific area, which is memory. Memory for a lot of these neural nets out there are known to be dominant. There's a lot of parameters to configure a neural network. You machine learning do training on these things, but there's a lot of parameters, which means a lot of memory that needs to be consumed. And the question is then, how do you manage that? How do you deploy something while maintaining the accuracy in which you need while reducing memory size? So these are kind of like the agenda for this presentation. We'll cover a little bit about the algorithmic development, right, to enable some of these tinyML. I'll talk about quantization specifically as an algorithm approach to enable this efficiency at the edge, right? Remember that there's other solutions out there, including pruning, this network architecture search. We'll focus only on quantization this talk within the time that we have provided, right? And we'll show a little bit about the things that we can achieve with Latent AI tools, but also and I kind of give a context of what are state-of-art kind of results that we'll show, right? And at the end, I would like to highlight some important use cases, kind of give a call to action for some of our folks to see what we can do with tinyML, given that you can make things efficient, given that you can deploy some of these neural networks with small memory footprint, right? What can it be enabled? So what this talk is about is giving you a highlight and give you almost a quick preview of what is capable, right? We're not going to go too deep into the actual algorithmic kind of approach because it's really complex and mathematically inclined. So for us here, just a quick preview and an understanding what can be achieved. And given that, what kind of things can we build? What kind of solutions can we build?
Hi, Sek. This is Ravi.
Yes.
Yeah, I just wanted to remind the audience to ask any questions in the Q&A session, and feel free to ask them during the middle of the talk. We want to keep this as interactive as possible. So if there are any questions about what Sek covered so far, please feel free to chime in. Thanks.
Yes, certainly. Yeah, thanks for that. Yeah, Ravi. Any questions? Certainly post them on the chat Q&A forum. Folks will be pulling it. Ravi will be kind of monitoring it and kind of ask me questions. And Ravi would also ask questions to help clarify some of these things. It's important to note that the quantization itself on the premise is easy, but there's a lot of ways to get good quantization results, right? Good ways to get the solutions that you want. So it can be complicated downstream. So I'm doing my best, hopefully, to not necessarily gloss over the topic, but give you a highlight of what it means and what you can achieve. So what we show here in terms of an introduction, right, for quantization is what does the algorithm really is about, right? And we talk in this slide here, talk about post-training. And from post-training perspective means you don't have to retrain your neural network. If you are already a trained neural network, what would you do in terms of reducing the memory footprint, right? So if you take a neural network and you look at any particular tensor, any particular layer, right? And there's a tensor that describes, let's say, the parameters, right? These are values that you have trained when you do machine learning training on them. And you look at the histogram of the values in the tensors and you plot it on your on a plot, right? For analysis. What you get is the top row, right? It's in the floating point range. There's some values, perhaps centered around 0. But the floating point axis has a long kind of range, right? Range from one end to the other end is quite large. And the goal in terms of quantization is to map that set of values to something smaller, maybe something that is representative with 8-bit integer. So we call it int8. And we want to find a transformation from the floating point axis to the integer axis. It's a mapping between one axis to the other axis. And the reason you do that is floating point may have the wide range, but a lot of your hardware may be doing int8 operations. You're doing byte level kind of operations. And you want to be able to squeeze all your workload and all your math functions really into the byte level kind of computation. So you do that set of mapping. As you know, because you're trying to, in a way, compressing from one domain to another domain, you may lose some accuracy there. You might lose some precision in terms of describing what is the shape in the floating point regime into the byte level regime. So the transformation, there might be some approximation in terms of your mapping. But you want to do a good enough job such that it doesn't affect the overall neural network computation, right? Such that you maintain your accuracy as you're doing inference at the end. So in terms of a post-training approach for quantization, you're looking at this kind of mapping. In the subsequent slide, I'll talk a little bit more about exactly and examples of what the algorithms might look like, how are different ways in which you can map floating point to integer. But the general premise of quantization is about looking at values and making a best guess about where it should be mapped to from one space to another. Okay.
So, quick
Yes.
question that came up.
Okay.
You mentioned there were other ways to compress a model, including pruning. There's a question about whether we should do pruning first or quantization first. Is there any preferred order for this?
I think there are no kind of general, best guideline kind of thing, right? I suspect that depending on the data set and depending on the model, one can go either way. A lot of folks do prune first before you quantize, right? Because a lot of folks that design neural networks, right, unless it's kind of really highly tuned, a lot of folks over parameterize your neural network. You just have a lot of nodes, a lot of layers, and a lot of connectivity, right? So as you do machine learning training, depending on how you trained it, you will find a lot of sparsity in your data set, right? You will find a lot of zeros in the weights that you want. You can go ahead and quantize, and you find that those are zeros anyway when you quantize, and then you can prune. The other way would be, say, I can prune it first and then quantize, right? Because you know those are values that you're not going to be using anyway, and that will help in terms of your algorithm for quantization, right? In terms of, hey, if you take 1 million parameters and you by pruning you cut it by half, the quantization algorithm would be greatly simplified in respect to looking at the number of values that it needs to, quantize over.
Got it. Thank you.
All right. And then moving forward in terms of quantization, let's look at training aware, right? What I've shown previously was a post-training quantization approach where you don't have to retrain the network. In this slide here, we talk about training aware, where you actually go in while you're doing machine learning training. You have a algorithmic kind of approach in there where you actually quantize as you go, right? You train in floating point, and maybe at every iteration or epoch, you say, well, maybe I need to quantize it to the desired range that I have, and then you evaluate and you repeat, right? This is the most basic algorithm. Other folks have, including ourselves, use other approaches in terms of training the neural network and quantize as you go. There's approaches in knowledge distillation, for example, and many others in the publication works and within tools that we have. But the most basic one is you just train, you have to understand how is it quantized to, evaluate, you repeat. I think the general idea about training aware quantization is that now that you are training the neural network, you have an additional dimension. The dimension is bit precision, meaning not only is your solution space searchable, and you can do machine learning to find that answer which gives you the best accuracy. Now you have an extra dimension with bit precision. Where do you want your solution in terms of the accuracy that you want, but also the bit precision, right? You could, for example, train in floating point 32-bit, floating point 16, 8-bit, and below, right? Some people have even trained, and ourselves included, train it to binary kind of values, right? In this case, the math and things like that will be much different when you go to binary. But those are kind of approaches which we take, right? That the actual solution space is not only just the right values for the network that you're training upon, but also the bit precision for each of those values, right? And there's different optimization points that we show. What we show in the graph here is that, yeah, the solution space is hyperdimensional, and you're finding a solution an accurate value, but actually an extra dimension, which is bit precision. So your search space can include kind of wider space because you have a bit precision in mind, right, in terms of finding that actual solution that you want. Okay. So the next slide here, quantization approach, I want to kind of go through and give some quick overview of some approaches that we are doing, right, that people have looked into. The most basic one in terms of quantization approach. So symmetric, asymmetric, and I'll talk about a few other. And these are terms that people use in the quantization realm, and these are algorithm in terms of mapping floating point, which is the top bar to the bottom bar. So you might have some values, for example, in the floating point domain. You have the max min range, some values in the middle, and the objective for, let's say, a symmetric quantization is to map that similarly to an integer space, right, which is the bottom kind of graph, right? So you're going from one floating point and then to another in integer space. In the symmetric kind of approach, everything is centered around zero, or you force it to be centered around zero. The reason is a lot of computation in terms of the convolutions and things like that are centered around zero because the filter weights are in a sense, bimodal and kind of map around zero. So it's naturally fitting for that. Some of hardware also have some special meaning for zero. It's actually more optimal to be centered around zero in terms of how they compute. So it sometimes makes sense in terms of using a symmetric quantization algorithm for that quantization approach. In the symmetric, asymmetric kind of approach, similar kind of idea. You have some values in the floating point domain, and you want to map it to the integer space, right? In this case, you're no longer centered around zero, but you can actually be any offset from zero. And this might make sense for other types of layer, right, within your neural network that allows you to kind of move between different kind of ranges, right? Not necessarily centered around zero. And then there's other approaches like logarithmic. And this is an interesting one where if you look at it, you may have some values in the floating point domain, again, spread over max and min kind of range. But in terms of mapping here, you go back into the integer space, but you go a logarithmic kind of approach. And you think of it as, things that are centered around zero are probably more directly mapped, but things that are on the fringe are actually mapped differently. Think of it almost like a fisheye lens, right? Things that in the center are less distorted, but it's kind of naturally mapped. But anything on the edge, you kind of have a curvature to it, right? You're trying to map more range that you can, but down to a powers of 2 kind of bins, right? So this allows you to have good fidelity around zero, because it's centered around zero. And then anything that is outside, you can able to kind of reach out further out to get the range that you want, right? So yet another kind of mapping approach. And I'm using that as an offset to the symmetric and asymmetric to show you that there's different ways in terms of mapping from one space to another space, right? And even given this approach, there are a lot of things in the academic domain, some in the production as well, including channel-based quantization, mixed precision, Hessian-aware, and many more, right? Many more that are available, right? And the trick about doing a lot of these work is to realize what can be used, when to use some of these approaches, right? And which one makes sense, right? And within the context of this presentation is to kind of just make you aware that, yeah, when we say post-training quantization, for example, you could take one of these algorithms. Don't be satisfied, because there might be other approaches that allows you to get a better solution. The most important thing I want to convey to the audience is that, what is the best approach, right? A lot of it depends on your network of choice, right? And the data that you have, right? If the data set is the things that you want to train upon is very simple, like meaning I can easily partition your data set, then any quantization algorithm will do well. But if you have a data set that is very hard to partition, right? There's a lot of mixed signals and things like that in there that are hard, then you might need some kind of heavy duty algorithm in terms of quantization. So there's no answer, because it depends really on your data set. One quick example would be if you look at MNIST data set, which is handwritten digits, or CFAR kind of data, very kind of small, simple kind of data set, very simple asymmetric algorithms will probably work well. When you get to ImageNet, 1,000 classes, lots of data, and even more complex data set that have visually similar kind of feature sets, right? A cat and a dog look very similar, for example, feature-wise. Those are harder, and you need more powerful algorithms. If you're doing post-training quantization, you need more complex algorithms and more capable ones to allow you to get to a good solution. Right? So with respect to post-training results, and we want to transition now from a mathematical and description of what the algorithm does. Let's look at some results, right? So post-training results, and let's just pick asymmetric for now in terms of analysis, right? What you see here is with a simple set of models, Inception, VGG, ResNet, we give a baseline floating point and then compare it with the, let's say, integer 8 quantization. So if you look at file size alone, you're seeing a 4x compression, right? Things that are represented in floating point 32, you need 32 bits to represent the value. You have a lot of range, right? But some of the range you don't need, right? And you can actually take that, convert it, map it using the quantization algorithms that I talked about, get to int8 space. And looking at the file size alone, you get a 4x reduction because int8 will be byte level compared to a floating point, which is 4 bytes. Right? So you get your automatic 4x compression. Most important, then you look at the accuracy, right? You do the mapping, and I talked about the mapping is really an approximation, your best approximation. The results are pretty good in terms of the network capability and also the quantization, right? You lose maybe 2 to 3% in terms of accuracy. In some cases, you may not, right? VGG 16, we may not push it hard enough in terms of the quantization. And for this particular example, not so good, right? So the point here is that, yes, this thing works. This thing, in terms of the quantization post-training, can get you to the compression that you want. It can also get you the accuracy. You got to be smart about picking the right algorithm and kind of tuning from there, right? And these are results that we have used with Latent AI tools with respect to quantization and providing the results that you have and running some of these networks both in the machine learning space, but also natively on hardware, all right? But there's also other tools, Google, PyTorch, all those folks have approaches that are provided in terms of quantization, right? So then let's look more in terms of the post-training quantization results, right? So in this case here, let's look at MobileNet, right? Let's take one particular class of models out there and say, okay, how do we do in terms of that particular network? Rather than going across different networks, let's look at one particular network. And I picked MobileNet because MobileNet is notoriously difficult to quantize using asymmetric. A lot of kind of publish annotations about, asymmetric doesn't really work well for MobileNet. And we agree, right? This answer here in terms of the table, if you look at the left table, MobileNet V1, if you use the, fourth roll down asymmetric into 8, right? When you quantize it with that algorithm, you get very poor top 1, top 5 result, right? It's just poor. Not because the algorithm doesn't work. I've shown you with the other network it does work, but with this particular network, there's different ways in which it uses the values in terms of how it's hand-tuned and created, right? It makes it hard for this algorithm. You can use other training, post-training quantization algorithms like the per channel kind of approach, and you get the accuracy back, right? You get the accuracy back because you have a different way of mapping some of the floating point into the integer space, and you get accuracies. If you look at the third row down per channel int8, very close to where the baseline floating point is, like negligible 1 to 2% kind of difference in terms of the accuracy. So pretty good result. If you look at inference per second, speed in terms of inference, right, compared to the accuracy, per channel might be a little bit not as good, let's say, compared to an asymmetric kind of result. And also, there's a trade-off there in terms of what you get in terms of accuracy versus inference. Now, that being said, right, selecting the right algorithms is going to be important for the model and the data set. We actually have other algorithms in which you have used, and we can get the same accuracy as the baseline and also get the inference speed that we want, right? If you look even on the MobileNet V2, similar kind of performance in terms of what it can do. Asymmetric doesn't work well as well. Per channel works well, but you suffer in terms of the inference speed. And our approach, we can actually get both the accuracy and the inference back up to a kind of top comparison. So if you look at just the MobileNet V2 alone, we can achieve the speed performance compared to an asymmetric approach. So if you just compare our approach versus the per channel, about 8x. If you just compare the a top 5 result of 125x in accuracy, right? The bottom line is for the takeaway from this slide, right, is to kind of convey to you that, yeah, you got to really select the right algorithm, right? Don't be satisfied with what is given. And you can actually do much with it in terms of getting the performance and also the inference speed that you want, right?
So I had a quick question.
Sure.
So when we move from FP32 to int8, generally we expect to see that the inference per second goes higher, right? In these tables you show, you actually it shows that it's slower in int8.
Right. So that's actually a very good question and a very good point that I wanted to make. If you look at the inference speed, as Ravi was saying, the baseline inference per second is quite high. And if you look at the int8 result, not as high as the floating point, right? One-to-one kind of mapping is not as fast. And you expect that, hey, if I'm going to byte level computation, you get harder. Well, a lot of it depends on the hardware. When you do comparisons, let's say for inference speed, latency of the inference, and power, for example, is very hardware dependent, right? In this case here, the format that we use, NHWC, number of, which really a number of batches, height, width, channel, that format in terms of how we store it doesn't work well for this particular hardware, right? Which is we're running on an x86 CPU. A different arrangement of that data format will give you better. Or the other way of saying, if you have a GPU or different type of hardware that's kind of targeting NHWC data format, you get the high speed back, right? So it's very hardware dependent. What we want to show here is that relative to each other, let's say relative to the byte level computation. So if you look at per channel, asymmetric, and our approach is at that range, it's comparable. But going from a baseline floating point to a byte level, then there's other effects in place, which includes memory, which includes the hardware and things like that. I will give you another example where if you're running on a, let's say an x86 compared to a Raspberry Pi, and you're looking at comparisons between floating point and integer. Well, bear in mind that the floating point unit in an x86, for example, is much different from a Raspberry Pi floating point unit, right? So the capability and the memory infrastructure with respect to the hardware is going to be important in terms of comparing, floating point versus integer, right? Because it's really at that point dealing with how do you map it to hardware and what are the formats that you use and what kind of accelerators that you have, right? Okay. And the talk here is really saying, hey, at least from the quantization perspective, you got to be smart in terms of how do you choose the right algorithm, and then the second after effects, which is let's pick the right hardware that matches how you want to store the formats. Okay. So we shift gear now to this slide, which talks about training aware, right? In this case here, we are actually going through the process of training the whole algorithm itself, right? And train as you and quantize along the way. We use an approach with using knowledge distillation, and we can actually take, for example, a neural network, train it, get a baseline result, and then we can look at whether we want to now quantize to int8, maybe using asymmetric kind of approach, or even a powers of 2 kind of approach. Now, bear in mind that the results shown here are map scores. So it's not accuracy, but map score with respect to the bounding box, right? Definition around the object of interest. So if it was a bicycle, you want to actually locate where is it in the image. So the scoring is different, right? In terms of the metric you use. So it's a mean average precision. In this example here, Pascal VOC, and the resolution we use is 224 by 224, right? Best in class that I've seen is about 0.7 for MobileNet V2 SSD, and folks might correct me in terms of what the result might be. And I would also qualify there's different published results in there with different resolution. So some have gone 512 by 512, 300 by 300. This is 224 by 224. Usually the higher resolution images tend to have a little bit higher accuracy, just because you have a little bit more context and a little bit more, um, features that you can pull out, right, in terms of analysis. But within the context, I think these are state of art. And what you see here in terms of the result, baseline to asymmetric to power of 2, is you can really maintain the accuracy, right? You look at the result from floating point 32, 0.634, to asymmetric 0.624, and even powers of 2 with 4 bits only encoded kind of result, 0.601, right? So really good result down to the 4-bit level using power of 2 kind of approach, right? And this is afforded with training aware. So training aware, the way we're doing it is finding the best optimal solution for the bit size that you want. So if you're trying to hit 4 bits, and you might try post-training quantization. If you're not satisfied with the result, you can go to training aware, where you actually go through the machine learning process to find a solution. And the solution includes looking at the bit precision dimension as well, finding where are the right points, right? And these are all tools generated with the Lainey AI tool. Again, other tool and frameworks also provide that, but some of these capabilities, including powers of 2 and things, are not necessarily readily available in other tools. Okay. And good to actually spend a little bit more time on this. If you look at the result, very interestingly, the ground truth on the bicycle floating point detection, right? 97%. Int8 was a little higher, 98, right? You said, well, how do you get more by quantizing? And in fact, you can get a little bit higher accuracy. You're redistributing some of these values around. Some classes might be, naturally better, but you might trade off other places as well, right? Similarly here, if you look at the bottom one, ground truth, and then FP32, and then to Int8, the floating point detection actually picked up the potted plant around 74% accurate. The Int8 one does not have that detection. So again, you're shifting the weights and distribution around to give you the optimal, but it's the best approximation to what a floating point might do, and as close as you can to the ground truth. Now, if what we've shown so far is quantization, both post-training and training aware, and what you see there is results that are pretty good, and these are things that are very complicated, right? You're talking about ImageNet 1,000 classes, and to be able to train and compress even down to 4 bits to get the results that you want. But is there more, right? And what we want to convey with this slide is that, yes, there's more things that you could do in terms of getting the efficiency, right? In this case here, we want to kind of showcase a little bit about a new technology that we are building called LeapAdapt. And the way it works is that you can actually get the neural network to automatically adjust what it needs, what performance it needs. What you show here in the video is that the network itself can throttle up and down. So U value here represents utilization. We can actually have the neural network throttle its utilization from anywhere from 30% to 100%, right? It determines where it needs. So in this video example, where you're doing let's say a left to right swipe or up and down kind of gesture, the neural network and the onset of it would run naturally in low utilization. Nothing is happening, so you don't need to start off very heavy. But as it starts to detect an onset of a gesture, an onset of something, it says, well, I need to have more confidence in terms of the results, right? Because something's happening, but I'm not doing very well in terms of recognizing what that might be. And then it would itself throttle up to the level that it needs, right? So in this case here, as it's doing, let's say, a gesture, a left to right or up and down, the throttle meter will go up, maybe up to 80% or 90%, and say, do I have enough confidence at that utilization? And it naturally goes up to a point where it says, okay, I'm highly confident now that this gesture is actually a, let's say a left or right or thumbs up kind of gesture. Then it will actually throttle back down because it now have completed the gesture, and then you kind of repeat, right? This case here, what we showcase with respect to the tinyML audience is that you can actually let the neural network decide where it needs to compute at in terms of its performance threshold, right? If the applications require you to run at a certain time at high utilization, you should. But when it doesn't need to, you don't need to run it that heavy, right? And these are another ways of saying you can actually have the neural network decide at runtime where it needs to run at. Right? And as opposed to saying, if I train a neural network today and I have to run and compute all of the nodes, that would be a kind of more of a static approach, and you're kind of bounded by the amount of computation that you need. In this case here, you actually training the neural network in a way that at runtime, you have the decision that you can make. In a lot of cases, this example here where we show a gesture recognition algorithm, you can throttle up and down because you leverage the time aspect in terms of a gesture. In other cases, for example, surveillance video, where you're analyzing, and detecting human presence and things. A lot of surveillance kind of videos are, in a sense, there's nothing happening in the scene. You don't need to run a heavy kind of workload. You can actually throttle down and actually ramp up when there's something happening in the scene, right? That, in a sense, for tinyML solutions, allow you to extend your battery life much more than just saying running it statically at 100% all the time, right? So this gives you another dimension in terms of what a actual runtime would be, right? Where you can actually have the neural network, your system solution, throttle up the utilization as needed, right? With minimal loss in the accuracy. And we think that something like this would be a game changer in a way, right? For a lot of tinyML solution, that you're no longer bounded by just what the neural network tells you you need to compute, right? If you're given 1 billion parameters, for example, and you say, well, at every instance when I need to compute it, I need to compute that 1 billion parameters, right? In terms of the network layers that you have to go through. The approach that we are taking is we actually deciding at runtime, maybe around 50% of that utilization, of the nodes that needs to be computed, and be smart about how you want to compute it, right? And given all that in context now, that you can quantize a neural network. You can do it post-training, or you can do it training aware. And you even have new kind of technology coming up in which you can dynamically throttle, right? Let's talk about an example use case, right? And that's important. What can tinyML allow you to do, right? What are some solutions out there? And I just picked this example as a starting point for a lot of folks, right? In terms of a discussion point. So for example, let's consider voice as a means for contactless UI. In today's scenario with COVID-19 kind of scenario things, right, where we're having lockdown things, nobody wants to touch anything because of contamination and what have you. Voice becomes a very useful means in terms of engaging systems, right? So voice as the context as UI. You have today, pervasive use, for example, with Siri, Alexa, those kind of things out there. So it's already coming, but let's make it smarter. Let's make it always on. There's privacy concerns about sending all your voice and sound data to the cloud. So tinyML solutions, because it's done at the edge, preserves all that privacy because nothing leaves your device, and you can doing it on premise. There's no internet connectivity needed when your processing is on the device. So it makes sense, tinyML solution as a contactless UI. In the picture, we showed maybe a kind of smart home box here, like an Alexa or a Google Home device. But it can be anywhere. It can be, think about an elevator shaft where you don't want to press the button, but you can actually voice it out. It can be a door lock. And, there's a lot of possibilities here. Suffice it to say, we looked into these kind of examples. We've done, let's say, 30 wake-up words, very small networks, compressed it. We've gone you've seen 5x kind of compression with the kind of audio recognition example, open source example there. We have done networks that are much smaller and shown 10x compression at 2 bits, right, for some of these networks, right? So very capable and things like that. What the tables show is a training-aware quantization approach, right? Because we're really trying to optimize it. We're getting about baseline 70% for 30 wake-up words. And we can, and I've shown you two level of results at using powers of 2, 6 bits. We get 77.1, so negligible kind of quantization effects. When you get down to 5 bits, you start seeing a dip in terms of the accuracy. And what we suspect as you go lower into 4 bits and 3 bits and things like that, it would start to tail off in terms of the accuracy. Right? You start to see the quantization effects there. But it's pretty low in terms of the bits that we can get to. And this is only the kind of start in terms of what we can explore, right? There's more capability in terms of what data sets that you want to look at, and also the type of models that you want, right? But the software solutions, the tools that are now available with respect to post-training quantization, with respect to training aware, and even kind of some of the new things coming on is starting to become available. And the use cases that we see here will be very capable, right, in terms of enabling some of these solutions. So what I'd like to do is end with a call to action, right? tinyML solutions can be very purposely well situated, purpose-driven, aligned to very worthy costs. You know, think about the pandemic situation, right? We can deploy a lot of these things, even for recovery, the recovery from lockdown, recovery from handling, saving more lives out there, right? And it's really a driver to make the world a better place. So I'm calling out to the audience, calling out to folks looking into tinyML to kind of do good things with respect to the technology that's coming available. We're opening it up with a tinyML survey just to understand where folks are in terms of developing some of these solutions, but really start to engage the audience in terms of what might be a good tinyML solution. Start the thought process, right, with respect to engaging among the community, but also deploying solutions that are out there, right? The link here is available as a QR or the bit.ly link, but is also available when the slides are posted up. You can look it up again. Okay. So with that in mind, and I'll move quickly to the next. I'm sure there's a lot of questions coming up. Thank you for the time. I'm hoping that you got a little bit out of the talk here, and you get the kind of the gist of tools and capabilities coming up. Very capable to make solutions that are meaningful for everybody to use, right? Any questions, contact me, my email, and general email here, but you know how to reach me, right?
Thank you very much, Sek. There are a lot of questions. I tried to answer a few, but in the interest of time, let's just go to the wrap-up slides, and then we can come back to the questions.
Certainly.
Thank you, audience. You will now see a 5-question poll pop up in front of you. Please take the poll as will help us keep improving our tinyML talks. And feel free to continue the conversation at tinyml.org/forums. You can ask new questions if you didn't have a chance to ask it here. The slides and video will also be posted there in the forums tomorrow. Just a reminder for the next talk on April 28th, the names of the speakers and the topics are here. We're trying a 2-speaker setting next time. So let me jump back into the questions, and Sek, feel free to move back to the slides that are relevant to the question you're answering. One of the most common questions that came up for multiple people is about the throttling and utilization. One question is, how do you define utilization? I'm just kind of moving back to that slide, if that's okay.
Sure.
How do you define utilization? And the other question is, how do you do the throttling? Like, is it with another network, or is it by changing quantization, or etc.?
Let me get to the right slide here. Can you go back to that slide, Ravi? Yeah, so there's a lot of things that one would say with respect to how this can be measured, right, metric-wise. I've seen a lot of I'll start generically and say a lot of folks have looked into performance-based metrics, right, for qualifying how well a tinyML solution might be. How small is it? How much memory are you using? How much power are you using? Those are still very static kind of things. The question is then when the system becomes dynamic, right? How do you really measure how well it does when it's the way it runs is context dependent, right? If you have a left to right gesture, you might have a different utilization compared to up and down kind of gesture. So it becomes a kind of new set of metrics, right? How well do you detect it? So I will generally say that the metrics itself, in terms of saying how well does a dynamic system work, are not kind of well set for neural network. The question about utilization then, the way we measure it is how many nodes, right, within the neural network, how much of the neurons, let's say, needs to be computed. So if it's really, when we say 50% utilization, it really means that out of the, let's say 1 million parameters, we are actually computing half of it, right? Half of the networks are actually active. The rest we don't worry about, right? We actually have a pseudo term. We say, well, maybe this is like dynamic pruning. When you statically prune it in terms of a training phase, right? You actually cut off the network layers to say, well, because I don't need this anymore. You actually chop it down so it becomes small. You can quantize and get to it. In this case here, you're doing dynamic pruning in the sense that you're not actually chopping it off, but at runtime, you decide what parts of the networks you don't want to run, right? You're gating those things off. Then the remaining is the one that you compute. And as long as you cover the right activation paths, you get a good enough answer. And this is what we're getting at, that a lot of the use cases here, we can actually eke out more performance in terms of the battery life and latency and things like that by being smart about how we compute, not necessarily chopping it off at training time. Make sense?
Yep, that's great. Thank you. Somebody asked about if there are any publications or references for this runtime scaling. If you have a chance, if you could post it on the forum response later, that would be really great.
Yeah, definitely would. There are a number of different publications, including ourselves, and we are putting more out there. A lot of them also have different terminology, right? That's becoming hard because this is so new. People have used throttling, people use gating, dynamic inference, a lot of different terminology. I would even argue papers are also getting hard because a lot of people are so set in how it's naturally computed today, which is running inference on everything, that once you start with something really new, it takes a while before it gets picked up. So there are pockets of different papers out there, and we will soon put something out as well. But definitely would like to share with other folks to kind of open up this space.
Thank you. Another question about, and this, a few different questions about this related to latent AI and whether you could do this adaptive AI with other open source tools than latent AI, or is this something custom, like at least what you're showing is something custom that latent AI is done?
Are there other tools? I'm not aware of any other tools that are publicly available or from an industry-based perspective. We are making this available soon. The thing about this is how do you make it more generic that it becomes a commonplace, right? If you look at where things are today, machine learning training, let's say CovNets and things like that, standard feed-forward networks, pretty standard. The folks in the AI community, knows how to use it. It's in deployment, very standard today. Quantization, training aware are starting to be that case, right? Still a lot of kind of basic knowledge and science to really get it out, but tools are starting to become available. These things for this dynamic thing are in the onset of being interesting and saying how does one A, deploy it, and B, making tools that are available. That's the harder part. The key thing here is not just that it can be dynamic, right? Is that for you as application developer to start to think about how else it would change your your solution space, right? Because at this point, you can think about not only running one, but you may run multiple, just because now you have the ability to kind of switch between one modality and another, to switch between utilization levels of one network. You can start to game up another network. It might make sense even thinking about when you have multimodal sensors. If you have, I'll just pick one, radar versus LiDAR versus um, visible, right, cameras, right? Let's say autonomous kind of systems, right? You have three different sensors, but you actually know in context what sensors should be more dominant in different scenarios, right? If it's rain, maybe some of these LiDAR radar makes more sense, or if it's different context, you might want to weight things differently. You can actually utilize your network differently. But what this dynamic system allows you to do then is make that decision at runtime, right? That it should be context dependent. So not only is it saying, hey, we want to develop these things and making it available, you're asking about tools, but also really push it from the application perspective, right? What should change in terms of how you deploy your systems?
Mm-hmm. Another related question about latent AI is like business model, or particularly what kind of hardware platforms do you develop these kind of adaptive AI like throttling networks for?
Right. Well, we're trying to be model agnostic, so we support a number of different models out there. We've shown the results there. We're also trying to be hardware agnostic, right? We'll support x86, ARM, a number of different platforms as well. For business kind of discussions, I'll defer it to one-on-one basis. We can actually contact us. We'll talk and go over that. But from a tool perspective, we are trying to be agnostic and work with any hardware out there. And we appreciate that within the tinyML community, there's a lot of different projects and systems being deployed, right? All of them different. All of them have particular use cases that are important, and we want to support all of them.
Okay, thank you. Another question about the audio wake word results, whether you have inference speeds for these results that you show here.
I have industry, but not shown here. For very tiny kind of systems for wake up things, it becomes very hardware dependent, right? Hardware dependent from really saying what does it make sense. That's why I didn't put the results here. We're working with a number of customers and folks that have solutions in this space. So I'm not really able to kind of show some of these results. But we're happy to talk to individually and see how we can help enable some of these solutions out there.
Okay. In the interest of time, we have a few other questions, about like 15 other questions on the Q&A. But what I can do is, as people might have time constraints, I'm going to just jump to the last part. But so other folks, please, I'll wrap up your questions into the forum, and Sek and I will go through and try to answer these questions in the next couple of days. But thank you, Sek, very much for a great talk. It was very informative. We really like the technical depth. Appreciate your talk.
Thank you, and I'll stay around for Q&A.
All right. Few other questions. Just a reminder to everyone, because more people are asking that in the chat. The slides and video will be available tomorrow. Please look at the forum at forums at tinyml, tinyml.org/forums, and any further questions we will take over there. So, Sek, you mentioned that you are available for a little bit longer for questions.
Sure.
So
yeah.
I will actually spend a few more minutes with the questions. One question is that's got popular is, can you please comment on quantization using low precision format beyond FP format for quantization, such as unum or posit instead of int8? I'm not fully familiar with these terminologies. If there's something that you've heard of.
Yeah, there's different folks looking at different formats as well. Int8 would be one. So that will be a sign kind of representation. So you have positive, negative. When you use asymmetric, for example, we go to uint8, so it would be unsigned, so that you don't have to carry the sign bit, so you get a little bit more. Some folks are looking at even more flexible floating point formats, right, to enable new hardware that can go between one and another. I still see this as a very kind of Wild West right now in respect to this space, right, in terms of storage format, in terms of the data precision, things like that. Still a little bit ad hoc in a way, compared to many different things that are a little bit more mature, for example, still a little bit out there. We have a lot of experience and things looking at different model formats, things like that, for example, TF Lite and things, right? So those are protobuf kind of based. Even those are I think, not necessarily standardized per se, right? So I'll just leave it as, yeah, there are, I think, standards being formed and people looking into it, but I don't see anything right now that says, this is the one that rules everything.
Got it. Another common question I think two or three people asked about this is, byte addressed, CPU or microcontroller, is it any beneficial to go less than 8 bits? If you go extreme binary, I know that there are specialized hardware to do like pop count and things like that. But if you go 5 or 6 bits, is that beneficial to do in a general microprocessor, or do you need custom hardware for this?
That's a very good question, right? You have byte level compute. A lot of folks are at byte boundary, and that's a very natural thing from the types of code that we have with respect to, our natural programming kind of constructs, right? When we program, people understand, even from the multimedia data set perspective, right? Byte level seems to work and work well. I've started to see a lot of activity going to 4 bits, right? Because you can train some of these neural network for very interesting applications at 4 bits, right? So you could do it at nibble level, right, 4 bits, and still get very tiny kind of solution. There's a lot of discussion about, well, why 4? Why not 5, right? Where do you draw the line, right? For a lot of microprocessor in there, you got to choose your powers of 2 kind of level, right? 8 bits, 4 bits, and I make sense. When you get to binary, of course, it's different. But if, for example, some of these solutions might have, this neural accelerators might have an FPGA or some sort of reconfigurable fabric, every single bit that you kind of carve out becomes resources for other things that are useful. So we don't necessarily, from our perspective, say we have to stop it at 8 bits. We can actually go below and kind of open it up, right? I also kind of convey that the idea for a lot of these quantization also is a design exploration kind of approach, right? So if you have a data set, you can certainly train a model on it and get to 8 bits, right? But what the engineer and us wants to know is what are some limits, right? And you can actually push the boundary and say, so how far before it actually drops off? Go below. So in terms of the capacity of the network, in terms of training upon that data set, and you go as far as you can. So if you go down to, for example, let's say 6 bits, a lot of these networks can sustain the accuracy at 6 bits. Your compute is at 8, but you go down to 6 bits. That tells you the level of confidence in terms of meeting, and adding more classes, right? Respect to that gap between 6 and 8 bits. So it's actually a tool that allows, from the data science perspective, to understand what some limits that one could use, right, and explore on.
Absolutely, makes sense. So in the slides that you showed, I think you talked about the weights being quantized. The activations are still full precision, or are they quantized as well in the slides you showed?
Right. So in the examples, everything can be quantized. So the first slide where I show results on the post-training, inception, VGG, everything is quantized, all activations, everything, and we're running at intake level. And the other slide where we had the mobile net one, the inference speed, everything is running at intake. That's why we're able to show the difference between performance, right, in terms of inference speed. And I mentioned that the hardware is dependent at that point in terms of the data format. So indeed, we're able to quantize everything.
Okay, excellent. We are 5 minutes over the hour. I think we've answered a lot of questions. We'll take up any remaining questions on the forums. Let's thank our speaker Sek again. Thank you very much, and thank you to all the audience.
All right, thank you.